Hi again, this is Mr. Pinter, your instructor for Signals and Systems. Welcome to part 2 of our lecture on chapter 1. In this part of the video, we'll be looking at real and complex exponential signals. Before we start talking about these exponential signals, I just want to mention that exponential signals are an extremely important class of signals for the study of signals and systems, because exponential signals are the solutions to differential equations which describe a lot of systems. So we'll be seeing this throughout the course. We'll be encountering these exponential signals. So let's start out by talking about a continuous time real exponential signal. So mathematically, our signal here can be represented by the function x of t, which is equal to c, some constant, we'll let that be a positive number, times e raised to the at. Now, the exponent here is some coefficient a multiplied by time. And a has, there's two options for a. It can be positive or negative. So when a is greater than 0, this is a growing exponential function. And when we plot it, it looks something like this. Of course, when we put in a 0 for t, remember that e to the 0 is 1. So our function gives us c, which is this number out in front here. And so that's plotted here, and then of course this thing grows exponentially. On the other hand, if a is less than 0, in other words, if we have a minus sign up here, like a minus 2t or something like that, this is a decaying exponential function, and it's going to look something like this. It gets smaller and decays exponentially with time. So here's a simple activity, just sort of like a warm-up for this part of the video. Go ahead and make a sketch of the following signal. X of t is equal to 5 times e to the minus t. So you don't have to do anything fancy here. Just make a quick sketch on a piece of paper or something like that. It doesn't even have to be graph paper. Go ahead and pause the video and sketch this, and we'll check your results. So here's the solution. If x of t is equal to 5 times e to the minus t, then the function is going to look something like this. Notice it passes through the value of 5 at t equals 0, and because there's a minus sign up here, this is a decaying exponential function, so it's going to eventually go to 0 for large values of t. The next important class of signals we're going to look at are exponential signals or functions that have a complex exponent. Okay, so before we dig into those, let's do a quick complex number review. And again, this is very fundamental information for this course. We're going to be dealing with complex numbers over and over in just about every chapter. So this is, should be a review for you. This is stuff you learned in your calculus class and so forth. But the good news is that pretty much everything you need to know about complex numbers is shown on this one page, but make sure that you understand this well in order to be able to do this course and be successful in this course. So let's just do the review here. So we can represent a complex number by any variable we want, but let's use the letter z here to represent our complex number. There are two forms that we can put the complex number in. There's the so-called polar form and the rectangular form. So the polar form has the magnitude out in front. I called it r here. So r is the magnitude of z. Okay, so I've got the, you can see the absolute value bars around z there. And then we have e raised to the j theta, where theta represents the phase angle. So the polar form basically is magnitude and phase of the complex number. Now, you may be wondering, what is this j here? Well, j is what your math textbook probably called I. It's the imaginary unit. Basically, it's the square root of -1. Now, why do we use j and not I? Well, electrical engineering textbooks tend to use j so that it's not to be confused with I, because current is represented by the letter I. So in this course, we will be using j, and you'll get used to that very quickly. Now, the other form that we can put this same number in is the rectangular form, which looks like a plus j times b, where a is the real part of the complex number and b is the so-called imaginary part of the complex number. Notice it has the j in front of it here. So one way to sort of reconcile these two different forms, they're obviously very different forms, but they represent the exact same thing. So how is this? Well, it's useful to plot z either as a point or even more, it's actually more illustrative to plot it as a vector in the so-called complex plane. So the complex plane, remember, this is the real axis down here, and the vertical axis is the so-called imaginary axis. So this real axis represents the real part of z. The vertical axis represents the imaginary part of z. So here is z. Z can be plotted as a point right here. Okay, let's say this is our value z. It has both real parts and imaginary parts. Or we can plot it as a vector. So let's take a look at these two forms. So in the polar form, remember r is the magnitude out in front. Well, that's just the magnitude of this vector. In other words, how long is this arrow right here? And theta, of course, is the phase angle, which represents the angle of this vector with respect to the real axis. So here are r and theta. This is the polar way to represent our complex number z. Now, of course, z can also be represented in the rectangular form, where a here is, if we project z down to the real axis, a is the real part of this z, and b is projected across to the imaginary axis. B is the imaginary part of z. So this picture here, as they say, is worth 1,000 words, because this tells you everything you could possibly want to know about this single complex number. It tells you its real part, its imaginary part, its magnitude, and its phase. And going further, we can relate the polar and rectangular forms by using basic trig. So trigonometry, notice this is a right triangle here, allows us to express r, theta, a, and b in terms of each other. So for example, this angle here, you remember from trig or math class, is the inverse tangent of the opposite side, which is b, right? This height here is b. And this length down here is a. So it's inverse tangent of b over a. So this is a relationship between theta and a and b. We can use the Pythagorean theorem to find out the value of r with respect to a and b. All right, so r is the square root of a squared plus b squared, again, because this is a right triangle. Furthermore, we can relate a down here is equal to r times the cosine of theta. So here's a nice relationship of how to find the value a if you know r and theta. So in other words, if you're given a complex number in polar form, it's very straightforward to find out the rectangular form by using a equals r cosine theta, and likewise b is equal to r sine theta. Now we can do something that's actually quite profound here. If we notice that z, remember our complex number in polar form, is given by r times e to the j theta, and we said that's equal to a plus b, where a is r cosine theta and b is r sine theta. Well, notice our rectangular form here, a plus jb, if we eliminate r, in other words, get rid of this r here, and this r here just by dividing, then what we're left with is the famous Euler's formula, which says that e to the j theta is equal to cosine theta plus j sine theta. And again, Euler's formula is something that we will be using fairly often in this course. Before we leave our review of complex numbers, there's one more slide here just on, this is sort of some special cases, and these are very convenient forms to use. So first of all, remember, if we take a complex number z and represent it in polar form as r times e to the j theta, there's a special case where we let r equal 1. And this is, r equal 1 refers to what we call as the unit circle. So this is a circle with a radius of 1. This r here, basically represents the radius of that circle. So when we set r equal to 1, then there are some special values here going around the circle that will come up now and then. So for example, if we have e to the j times 2 pi, all right, or e to the j 4 pi. Well, remember, we start here. If we go around 2 pi, we end up right back here. If we go around another 2 pi, so we've gone around 4 pi radians now, we still end up back here. And this is the same as e to the 0. All right, 0 radians is the same as 2 pi radians, because 0 radians, that means theta is 0. We're right here at +1. And if we go around, we're back at +1. So these forms up here, if ever we see those forms, obviously they are just equal to 1. Now look at this point up here. Well, this has an angle of 90 degrees, which is pi over 2. So e to the j pi over 2 is up here, and that's equal to j. That's equal to positive j. Right? It's a purely imaginary number. Likewise, instead of going up by pi over 2, if we go down and around by 3 pi over 2, which is 270 degrees, we also end up at j. So these two expressions here, even though they look very different, they are identical to each other and they're equal to the value of j. Likewise, when we start here and we go by a full pi radians over here, 180 degrees, we go from +1 all the way to -1. So e to the plus or minus j pi is equal to e plus or minus j 3 pi, 5 pi, so on and so forth, and they're all equal to -1. And our last special case is down here. If we go down by pi over 2, in other words, negative pi over 2 radians, we end up at -j. Or we can go in the positive direction, 3 pi over 2. Okay, so all of these forms here can be simplified to very basic fundamental numbers, either 1, plus or minus 1, or plus or minus j. So now that we've completed our review of complex numbers, we're ready to dig into complex exponential or imaginary exponential signals. And we're doing this for continuous time first. We'll deal with discrete time later. So the general form is, this looks familiar. This is our exponential signal again. X of t equals c e to the at. The only difference now, and it's a big difference, is that a is not a real number like it was earlier. Now a is going to be purely imaginary. In other words, it has no real part. It's just got the j times some number, and that number we're going to call omega, and you'll see why shortly. So substituting this into here, we see that our imaginary exponential signal is x of t is equal to some constant c times e to the j omega t. And what we can do is invoke Euler's formula. Remember, Euler's formula says if we have e to the j something, that's equal to cosine something plus j sine something. So by plugging this into Euler's formula, x of t can be written as c times cosine omega t plus j times c sine of omega t. So let's look at the real part of this function. There's a real part here, and this is the imaginary part because it's got that j in front of it. But the real part of this function is just a cosine function. It's oscillating. It's an oscillating function. So if we were to plot the real part, all right, of x of t, that's what this means, the RE for real part of x of t, it's going to look something like this. It's a cosine function. And likewise, the imaginary part oscillates also. And notice it oscillates at the frequency given by omega, where omega was up here in between the j and the t. So that is our radian frequency. So this provides us an easy way to find the radian frequency of a periodic signal just by inspection. So if we ever see, some form like a times cosine omega t, or a times sine omega t, or a times e to the j omega t, in all cases here, the number in front of the t, and in this case, it's in between the j and the t, that number gives us the radian frequency. So the radian frequency, omega, is, of course, in radians per second. We can convert that to so sometimes they call this the physical frequency, f, which is equal to omega divided by 2 pi, because remember there are 2 pi radians per going around the circle, there are 2 pi radians per cycle. So the physical frequency is given not in radians per second, but in cycles per second. And this is also known as a hertz. The unit hertz, or Hz, is when we're talking about the physical frequency. The period of this signal here, t, is equal to 1 over the frequency. You'll remember that from your physics class when you learn about waves. And that is equal to 2 pi over omega if you're going to use omega instead of f. And the period, of course, has units of seconds. And finally, the amplitude of this signal here is given by whatever this number is out in front of the sine or the cosine or the complex exponential. Notice in all these cases here, the amplitude is designated by A, and if it's shown like this, in this form, you would say the amplitude is equal to C. So here's an example or an activity for you to practice what we just learned. So let's say you're given the following signal. X of t is equal to 5 cosine of 6 pi t. So your task is to find the amplitude, the radian frequency, the physical frequency, and the period of this signal right here. And just to make this a little bit easier so you don't have to go back to the previous slide, I put all the equations here to figure out these various parameters down here. So again, go ahead and pause the video and see if you can figure out what these are, what A, omega, F, and T are for this signal here. All right, so the solutions here, the amplitude is found just by inspection, that's 5. The radian frequency is also found by inspection. Remember, omega is the number that is multiplying in front of t. So omega is equal to 6 pi, and the units, of course, are radians per second. The physical frequency we get from just taking omega, which is 6 pi, and dividing it by 2 pi. So we get 3 cycles per second. And finally, the period t is just 1 over f, so we have 1 over 3 gives us 1/3, or 0.333 seconds. Let's now take a look at a more general type of continuous time complex exponential function. This time we're going to start, pretty much with the same form. X of t is equal to c times e to the at. But now, instead of a being purely imaginary, a is going to be complex. In other words, a is going to have a real part and an imaginary part. And also, just to make things completely general here, let's let this number out in front, c, also be a complex number. It's not just a real number anymore. So the trick to making some sense of this is to let this c here be in polar form. So we're going to let c equal to the magnitude of c, because remember c is complex, times e to the j theta, where theta is the phase and this is the magnitude of c. And then we're going to let a, which is up here in the exponent, we're going to let that one be in rectangular form. So we're going to let a equal sigma plus j omega, where sigma is the real part and omega is the imaginary part. So when we substitute these expressions here for a and c into this up here, we get the following. X of t is equal to magnitude c times e to the j theta times e to the quantity sigma plus j omega and the quantity times time. Now, what we need to do, we can lump together all the real parts. So the real part here is obviously the magnitude of c is real. And also, remember, sigma is a real number. So e to the sigma times t is also a real quantity. All right, this is just an exponential function. There's no j or anything in it, okay? So we're going to lump these two real terms together, and they constitute what is called the envelope of this function. Now what's left are the imaginary parts. We have e to the j theta, and we have e to the j omega t. So I'm going to factor out the j, and in parentheses I have omega t plus theta. So what these mean now is that omega is still the frequency. It's the radian frequency because it's the number that is in front of the t. The theta here is what's called a phase constant. Okay, it's not related to the frequency, but it determines sort of where this function starts at time 0. And furthermore, this sigma, going back to our real part here, the envelope, the sigma is related to the time constant of how fast this signal either grows or decays. In fact, sigma is 1 over the time constant. So let's look at a couple different cases here. If sigma is a positive number, all right, sigma greater than 0, then this envelope here is a growing function. In other words, the amplitude of this signal is getting bigger with time. So that's represented by these dotted lines. Notice the amplitude is growing. And an example of this is in resonance. When we have resonance, we have a signal that grows with time, an oscillating signal that grows in time. Now notice the actual signal, though, is oscillating up and down. Now why is that? Well, because of this portion. This complex exponential here, remember this is e to the j omega t, and then there's a phase constant. But the e to the j omega t, remember, is oscillating. It has a cosine and a sine involved with it. So this is what this signal would look like for a positive value of sigma. It is a growing, an oscillating function that is growing with time. The other case, of course, is when sigma here is a negative number, then our envelope is decaying with time. It's getting smaller and smaller, and we have an oscillating signal that is, decaying with time. An example of this would be damped harmonic motion or damped oscillations due to, say, friction. So let's take a look at a couple of examples. Before we do, in fact, these are activities for you to figure out here. You can do these on your own, and then we'll look at the solutions. So I put the expression from the last page here to help us kind of remember what's what. So for this first example, y of t is equal to 12 times e to the j 5 plus 2, all in parentheses, times t. So the question is, what is omega? What is the phase constant? And then is the amplitude constant, decreasing, or increasing with time? The next example, x of t is equal to 7 times e to the 3j times e to the j 2t. So again, what is omega? What is the phase constant? And what's happening with the amplitude? Is it constant? Is it getting smaller? Or is it getting bigger with time? So go ahead and, again, pause the video and see if you can figure these out on your own, and we'll check it soon. So here are our solutions to the example. So for the first one, what is omega? Well, the trick to doing these, I think, is so you'll be less likely to make an error, is to take our original signal here and let's factor in the t. So we have 12 times e to the 2t times e to the j 5t. Okay, now one thing we can do here is we can immediately see that the 5 is multiplying the t, so that gives us our omega. Now what is the phase constant? Well, there is none in this form. Notice, if we compare this to up here, you can think of this 5t here is the same as 5t plus 0. So now it looks exactly like this form up here, and you can see that theta is indeed 0. Now what about the amplitude? Well, what we have to look at is the real stuff out in front. So we have the 12, and then what's important is we have the e to the 2t. This is an increasing function with time, so our amplitude is increasing. For the second one down here, what I'm going to do is sort of the opposite. I'm going to take these two forms here, and I'm going to combine them, all right, by using our rules for exponents. Remember, when we have two numbers like this multiplied together, we simply add the exponents together. So when we add these together, I can factor out a j, and I get 2t plus 3. And now it's pretty simple to see that omega is the number in front of t, it's 2. And our phase constant theta is the 3 here. All right, again, I'm looking at this up here for reference. Theta is 3 radians. And then the amplitude, notice, is just 7. There's a 7 out here all by itself. So that is a constant amplitude that's not changing with time. Let's now turn to real and complex discrete time exponential signals. So we'll start with discrete time real exponential sequence. We can write it mathematically as x of n. Remember, sequences have the index n inside of those square brackets there, is equal to c, we're going to let c be a real number, times alpha, which is sort of the base here, and we'll let alpha, in this case, be a real number also. And alpha is raised to the n. Remember, n is kind of like our time variable here. So there are a bunch of different cases here depending on the value of alpha here. So let's take the first case where alpha is greater than 1. Okay, so alpha could be 2, 3, 4, something like that, or it could even be a fraction like 1.5 or something like that. Well, if this number is greater than 1 and we're raising it to the nth power, then we have a sequence that is growing exponentially like this. So this would be x of n. On the other hand, if alpha is between 0 and 1, okay, like alpha is 1/2 or 0.7 or something like that, then as we raise this number, alpha, to a higher power, it's going to get smaller and smaller because alpha is less than 1. And so this would represent the case where we have exponential decay when alpha is between 0 and 1. Now, what about alpha for negative values? Well, here things get a little more crazy, because if alpha is a negative number, then remember n is an integer. So n, goes 1, 2, 3, 4, 5. But when we square a negative number, it's positive. But if we raise a negative number to an odd power, it's negative. So in other words, even powers of alpha, or when n is even, are positive, and when n is an odd number, designating an odd power, our sequence is going to be negative. So what we see is the sequence actually alternates. It goes positive, negative, and in this case, alpha is between -1 and 0, so it's an alternating exponential decay. And if alpha is less than -1, for example, if alpha is -2, -3, whatever, then we have an alternating exponential growth. And again, notice that our sequence, x of n, alternates between positive and negative values as it grows. So here is an activity for you to practice. Go ahead and make a sketch of x of n, which is equal to 1/2 to the n, from the values of n equal -2 to n equal 2. So go ahead and pause the video and do this activity. So here's our solution. Remember, what we can do here is, if we're going to start, let's start at n equal -2. So we have 1/2 to the -2 power. So remember, a negative exponent means you take the reciprocal of whatever you're, raising it, whatever you're raising. So the reciprocal of 2, the reciprocal of 1/2 is 2. So 1/2 to the -2 is the same as 2 squared, which is 4. All right, and so that's how you do the -1. So this sequence then, when n is -2, it has a value of 4, and then it goes 2, 1, 1/2, and 1/4. So if you didn't get that, make sure you go back right now and make sure that you can redo this and understand this. Let's now move on to discrete time imaginary exponential sequences. And again, this is something that we're going to encounter in this course later on. So this is why we're learning about these now. So in this case, we have a sequence x of n that is described by the function e to the an, where a is a purely imaginary number, like j omega. And again, we're using omega because this is going to turn out to be the frequency of this signal. So let's substitute j omega for a, put it in there, and we have e to the j omega n. And now we can use Euler's formula to write this out in terms of cosines and sines. So this is equal to cosine omega n plus j sine omega n. And here again, we see that this complex exponential sequence here is going to be oscillating. All right, this thing is represented, the real part is represented by a cosine function, cosine omega n. And also remember that n here is our index, all right, like our time index, but it really doesn't have, it's not time because it's a dimensionless integer. It doesn't carry any units. Likewise, omega, even though we sort of call it our frequency here, we have to be careful. It really represents an angle in radians. All right. Now, there's something else that is sort of maybe a little bit surprising about this function, cosine omega n. Now, cosine omega n, it clearly oscillates, just like cosine of omega t would. However, this may not be a periodic function. So, if you're wondering, well, if it oscillates, then doesn't it have to be periodic? Well, the answer there is no, and we'll investigate this next. So let's take a look at, let's go back to continuous time. If I have a function x of t is equal to cosine times t over 6, and that's plotted here, all right, remember this is a continuous time function here. Well then, by inspection, I can see that my frequency is the number in front of the t, all right, so it's 1/6. And that's my omega, my radian frequency. The physical frequency is then omega divided by 2 pi, which is 1 over 12 pi, because remember, omega is 1/6. So my frequency is 1 over 12 pi. The period of this function here is equal to 1 over the frequency. So we take the reciprocal of 1 over 12 pi, and we get a period of 12 pi. And of course, this function is periodic because it repeats itself over and over every 12 pi seconds. However, let's take a look at x of n is equal to cosine of n over 6. So notice this is sort of like the discrete time version of this. We're just replacing t over here with n, right? The t right here becomes an n here. Well, if we plot it, okay, it looks like a cosine function. It goes up and down and up and down. However, it's not periodic. It doesn't exactly repeat itself, okay? And the one way to show this is that, notice by inspection here, again, omega is 1/6 because omega, remembers, the number in front of the n. The frequency then is omega over 2 pi, which is 1 over 12 pi, all right? Nothing different. That's exactly what we did here. And the period, which by the way, when we talk about periods in discrete time, we're going to use the uppercase n instead of the uppercase t. Well, the period is always 1 over the frequency, and that gives us 12 pi. But here's a problem. 12 pi for a period is not an integer. And remember, a discrete time sequence has, for its index, it has to be an integer. In other words, n equals 0, 1, 2, 3, 4, 5, 6, and so forth. N is never equal to 12 pi, right? Because it's not an integer. So this is one way of showing that this thing is not periodic. It doesn't exactly repeat itself. Here's another, maybe a little more better, more clear way to see that not all oscillating sequences are periodic. So this is an example of a non-periodic sequence. So our sequence that I plotted here in Excel is very simple. It's x of n is equal to cosine of n over 2. So, here's n. I went from 0 out to 40. And here's the values of x of n. And you can see they're plotted here. So, if we kind of think of connecting the dots, we can obviously see this is a nice cosine function. Okay, everything looks fine and dandy. However, this thing never repeats itself. Notice up here at the peak, notice the placement of these two parts of the sequence. Well, on the next cycle over here, they're in different places. They've shifted over. And over here, they look kind of close to that, but it's not. They're always shifted slightly from each other, and it'll never, ever repeat itself. You could look at, 100 million cycles of this thing, and some of the values may get very, very close, but it will never actually repeat itself. So this is an example where we have a sinusoidal signal or graph, but it is not periodic. So the question now becomes, is there such thing as a periodic discrete time sequence? And the answer is yes. However, there is a special periodicity requirement that has to be met in order for a discrete time sequence to be periodic. And this is the way you can prove and derive this. You're welcome to go through this yourself. It's nothing that difficult here. We're just basically what we're doing is imposing the periodicity requirement that a sequence is periodic if x of n plus the period n is equal to x of n. In other words, it has to have the same exact value as x of n when we add the period to it. Okay, and again, is our discrete time period. It has to be, remember, an integer value. Okay, so when you go through all the math here, you'll end up with this requirement. This is the important thing. This is like the test. The period of our signal or sequence, n, has to be equal to 2 pi times m over omega. Now we know what omega is. Omega is the frequency of our signal, which we can get, by just inspection, by looking at it. M is the smallest non-zero integer needed to make n an integer. So in other words, if we can find a value of m, and remember m has to be 1, 2, 3, 4, 5, 6, 7, one of the integers, all right, not 0. If we can find a value of m that makes n an integer, then we have a periodic sequence. So let's look at some examples. So we're going to show how to find the frequency and period of a discrete time sequence. So finding the frequency omega is pretty straightforward by inspection. So in other words, if we have cosine of omega n, well, the frequency is just this, whatever that number is, omega. If we have sine of omega n, again, we use whatever's in front of the n. Or if we have it in complex exponential form, like e to the j omega n, again, the omega is the number right in front of the n there. So for example, if x of n is equal to cosine of 7 pi n over 3, then just by inspection here, I can immediately see that omega is 7 pi over 3, because that's what's multiplying n right here. Now, to find the period, remember what I have to do is I have to set n equal 2 pi m over omega, all right? And I have to try to find a value of m that makes n an integer. So let's see if we can do it. So what is omega down here? Well, we said omega was 7 pi over 3. So I'm going to plug that in here. So here's the 7 pi, and I put the 3 up here. So notice this 3 up here and the 2 multiply together to get 6. Notice the other thing, and this is kind of the key thing. This pi up here, which we started with here, cancels the pi down there. So when those cancel out, we're left with 6m over 7. Now, can we turn this fraction into an integer? Yes. Just sort of by trial and error, you can see that if you let m equal to 7, it cancels the 7 down here, and we're left with n, our period, is equal to 6 right here. Okay, so this signal right here, this sequence, has a frequency of 7 pi over 3, and it has a period of 6, meaning it repeats itself every 6 values. So finding the period is, not quite as obvious. You can't do it just by inspection. It's nothing obvious there. You have to apply this test here. Here's another example. X of n is equal to sine of 2 pi n over 12 plus 1. So let's do this again. So first of all, let's find the omega. Well, remember the omega is whatever is multiplying n. So that's the 2 pi over 12, which we can simplify to pi over 6. Now, to find the period, n, we have to set it equal to 2 pi m over omega, where remember omega is pi over 6, so I'm going to plug that in. Here's the pi. I put the 6 up here. This 6 and that 2 multiply together to get 12. This pi on top cancels this pi on the bottom, so I get 12m over 1, which is, of course, just equal to 12m. And obviously, I can find that m, the lowest possible number to make this an integer, is when m is equal to 1. And so, therefore, our period is n equal 12. And this is the function plotted here. Okay, so in other words, this sequence up here is plotted right here, and you can see that this thing repeats itself every 12 values. If you count, so let's say you start here, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and at 12 we're back to where we started from. So here's a chance for you to practice these techniques. Go ahead and do these activities. For each of these, you're asked to calculate the amplitude, the frequency, and the period for the following discrete time sequences. There's two examples here, and you may need to go back to the previous, go back in the video to the last slide, especially to find the period. You have to apply that technique there. So go ahead and give these a try. All right, so here are the activity solutions. For the first one here, by inspection, we can see that omega is just pi over 8. And then to find the period, we say n is equal to 2 pi m over omega, where omega is pi over 8. So here's the pi, here's the 8. 8 times 2 is 16. The pi's cancel, so I get 16m. And the lowest value of m to make this an integer is, of course, m equal 1, which gives us our period of n is equal to 16. All right, and that is plotted right here. The next one here, x of n equals cosine 3 pi n over 2 plus 5. Again, by inspection, I can see that omega is 3 pi over 2. That's just the stuff in front of the n there. We don't need to worry about this 5. And to figure out the period, we set n equal 2 pi m over omega. We plug in omega, which is 3 pi over 2. Simplify, right? Multiply 2 times 2 is 4. The pi's cancel. We have 4m over 3. The smallest value of m that makes this an integer is m equal 3, which gives us our period of 4. And by the way, this sequence is plotted right here, and you can see this thing repeat itself every 4 values because that's the fundamental period of this sequence. In this section, we're going to look at the concept of discrete time frequency in a little more detail, as there are some subtle and important differences in frequency between discrete time and continuous time signals. So this whole concept of discrete time frequency is kind of interesting because if we consider, let's say our sequence x of n is equal to cosine of omega n. This is, a cosine function that's obviously oscillating with a frequency of omega. But in discrete time, omega is actually an angle in radians. It's not really a frequency, because the reason for this, is, again, it's kind of subtle. This n here is sort of like t, like time, except n is a dimensionless integer. It's just an index. It doesn't carry the units of time. So remember that, the argument of a cosine function has to be an angle. So omega times n has to be in radians, and therefore omega has to be radians. So omega technically is just an angle. It's not really a frequency. Now, what's significant about this is that, remember, angles only vary from 0 to 2 pi before they repeat themselves. In other words, theta and theta plus 2 pi are the exact same angle. So, we can see this on the circle here. If this represents the angle theta right here, if we add 2 pi to that angle, we go all the way around the circle and we end up right back to where we started from. So what's kind of weird about this is that this, when we talk about, cosine of omega n, first of all, this frequency omega can only go from 0 to 2 pi, and if we go above 2 pi, we can always subtract the 2 pi to get back to the same frequency. So, there's some significant differences here. In continuous time, the frequencies range from 0 to infinity, and they can have any value, all right, from 0 to infinity. But in discrete time, frequencies range from 0 to 2 pi only. There is no other frequency beyond, this range of just from 0 to 2 pi. If you do have a frequency higher than that, you can always basically simplify it back to one of the angles around on the circle, which is, from 0 to 2 pi. Oftentimes, the frequencies are said to range from negative pi to positive pi. And, notice, though, this is still a total frequency range of only 2 pi. This is sometimes a more convenient way to think about it. So let's dig into this discrete time frequency a little bit more. And, notice I kind of put it in quotes here because although, we call it a discrete time frequency, remember it really represents an angle that repeats itself. Now, the thing is about this, let's plot our cosine function, cosine of omega n. Let's plot it for a bunch of different values of omega. So if we let omega equal 0, well, cosine of 0 times n is just the cosine of 0, which is 1. So here's the sequence. This is x of n, which has no frequency. Now, this makes sense. If it has no frequency, then it never changes, and it's just a constant value. So this is what, really a really low frequency signal would look like. Basically, it's not changing at all. So that all makes sense. This is cosine of pi n over 8, so we have a frequency of 1/8. All right, and so now you can see it oscillating up and down. Here's cosine of pi n over 4. So here the frequency was pi over 8. Here it's pi over 4. So this has twice the frequency of this one. You can see it's wiggling up and down twice as often, all right, twice as fast. And then we have cosine of pi n over 2. So now it's oscillating, even faster than this one, twice as fast again. And then finally, look at this one. Here's cosine of pi n. So the frequency here, omega, if you can do it by inspection, is pi. But look what's happening. This thing is oscillating up and down as fast as it possibly can. It's going from max value to min value back to max. You can't go any faster than that, right? That's the fastest it can possibly oscillate. So what this tells us, oh, and then by the way, if we keep going, notice it starts slowing down again, and when we get back to 2 pi, we're back to our signal that doesn't oscillate at all, because remember, 2 pi is the same as 0. So what this tells us is that with discrete time, a frequency of 0 or 2 pi or 4 pi or any multiple of 2 pi represents a low frequency with slow variation, and a frequency of pi or 3 pi or 5 pi is the highest possible frequency that represents rapid variation, and that was the image shown in here. So this is, again, kind of a little different from continuous time. It's actually very different. Frequencies can only vary from 0 to 2 pi. There's nothing else that's possible for a discrete time sequence. There's one more really meaningful concept about discrete time frequency, and this is actually not really shown in your book. It may be mentioned much later in your book in chapter 7 on sampling, but your book doesn't really stress this concept, but I like to include it here because I think it gives some good insight into visualizing and thinking about what a discrete time frequency is. And that is, we can think of it as radians per sample, because really that, in a sense, that's what it means. So let's start with the sinusoidal continuous time signal, which is this red line here. Let's call it x of t is equal to sine of omega t. And what we're going to do is we're going to take samples of this signal every sampling period. Okay, so we're going to sample x of t with a sampling period of t sub s to generate the sequence x of n. So our sequence now are these black dots here. This represents our sampled version, or now we have a discrete time sequence. So if we plot x of t and x of n again here, you can see them again, but instead of plotting them versus time here, or versus n, we're going to plot them versus their phase. Remember, one full cycle is 2 pi radians. So in other words, this is phase here. So we have 0 here, and when we've gone around one full cycle, and we're back to where we started, that would be 2 pi radians. All right, so halfway through is pi radians, and then a quarter way is pi over 2, 1/8 way through is pi over 4. So this is just, the same graph up here, but we're plotting it versus the phase of the cycle here. So the discrete time frequency, omega, the little d under there for discrete, it tells us how many radians per sample there are. And we can see that each one of these samples is pi over 4 radians, all right? And so the way to get from one to the other is we notice that radians per sample is equal to radians per second times seconds per sample, all right? Because these seconds cancel right here. So radians per sample, that is our discrete time frequency, omega sub d. Radians per second, that is our continuous time frequency, omega. And finally, seconds per sample, well, that's just the sample period, t sub s, right? That's how many seconds it took for each of these samples to take place. So what we end up with is a way to there's a couple things here. First of all, it tells us that discrete time frequency carries the units really of radians per sample, even though technically it's just radians. And also, we can get the discrete time frequency by multiplying the continuous time frequency by the sample period that was used to create the sequence. So here's an example. In fact, this is the last thing we'll do in this part of the lecture here. We have a 2 megahertz continuous time signal, that's the red line here, and we're told that it's sampled at 10 million samples per second. What is the frequency of the resulting discrete time sequence? Okay, so I put all the equations that you should need to solve this activity, to do this activity right here. So go ahead and see if you can figure out, basically we're taking this 2 megahertz signal here, the red line, and we're turning it into this sequence, which are the black dots. But we want to know what is the frequency of this sequence when we're all said and done. So again, go ahead and pause your video and see if you can do this activity. All right, so here's the solution to our activity. So again, we've got this 2 megahertz continuous time signal. It's sampled at 10 million samples per second. We want to figure out what is the frequency of the resulting discrete time sequence. So we know that our sampling frequency, f sub s, we're doing 10 million samples per second. So that's 10 to the 7th samples per second. So our sample period, t sub s, is 1 over the sampling frequency. So 1 over 10 to the 7th just gives us 10 to the minus 7, and you can see that's 10 to the minus 7 seconds per sample. So in other words, we have this is a 1/10 of a microsecond per sample. All right, we can figure out what omega is. Well, remember, this is continuous time now. Omega is just 2 pi f, so we have 2 pi radians per cycle times 2 times 10 to the 6th cycles per second. Where did I get this number? Well, that was given to us, all right, 2 megahertz. So that's equal to 1.26 times 10 to the 7th radians per second. Finally, we use our equation that we were told. The discrete frequency, omega sub d, is equal to the continuous frequency, omega, times the sample period. So I have 1.26 times 10 to the 7th radians per second times 10 to the minus 7 seconds per sample. We multiply these together. Actually, you can do this in your head. You can see these exponents cancel each other. And we end up with 1.26 radians per sample. So notice that this number here, 1.26, is less than 2 pi, right? 2 pi is around 6. So this original signal, which had a high frequency of 2 million hertz, when we sample it, the sample frequency the sequence frequency, the discrete time frequency of the resulting sequence, is only 1.26 radians per sample. Okay, so that is it for part 2 of this lecture. We will continue on, and I'll see you in part 3. Goodbye.